Is your card menu? Your card? Oh, wow.
That's probably why if you see me like drive around, it's always out. I don't mind waiting for the crosswalk, so I just do that as the start. It's not like it's doing a good mind, I mean, you guys push all the way in and just short.
I go over here quick.
Well, then it's just gonna jump. You know, I always try to be self-aware for one
I'm gonna take you. Start in a second.
I've done it a few times. Anywhere I'm at, like if I'm in an intersection, I'm just starting in a second. So I gotta take the turn quickly.
That's good.
I've done it a few times when I talk to it. I don't know, but I just sometimes I'm not sure who Red Bull like watches. Yeah, I guess I know. Yeah, because for like 6 years and like 3 seconds, you know.
Man, it's nice to have a mostly full room of students, mostly full class. Seems like they're dropping like flies pretty much everywhere else. I'm happy that you guys are all still here. Because of seniors, because of basketball teams, because of all kinds of stuff. I have in literally every other one of my classes. Well, I have at least one student who's out on COVID quarantine in every single class. And most classes I have at least 2 that are out on quarantine. So that leads me into this. If you haven't gotten your first COVID shot yet, COVID vaccines are giving them out today at 3:30 to 5:30 here at the school. Bring a parent, get the thing signed. Basically, you just need to bring this form signed by your parents, actually. If you need a copy of it, I have some copies. Anyways, I don't know, let's see. I wanted to actually kind of pick up at the end. Yesterday, we just didn't quite have time to get through all the slides that I showed you guys with the Columbia River basalts. And I'm not sure if the projector is quite ready to function or not. Nope, not yet. So our goal today, Columbia River Basalts 2, today is mostly going to be interpretations. We got a bunch of field data. We described what you can find. You can go out in the field in Eastern Washington, in Eastern Oregon, and find these basalts, find these different flows, these different formations. And that was a lot of what it is, but there wasn't really any why it is. The why, I mean, we talked about the why of like vesicles and pillow basalts and stuff like that. But we did not talk about why we have a Hawaiian island's worth of basalt sitting here on land. This is the rock that makes up ocean floor, but this is not the ocean floor. So that's what we're doing with most of today. I really want this damn Apple TV to start being willing to talk to devices so I can finish showing you these slides. Because we got a couple of nice maps and a couple of things that we didn't really get to yet. I meant to turn this on earlier, so if you're ready to go, but I just did. But a little bonus thing here. So I told you guys yesterday that in Tri-Cities, hey, there we go. In Tri-Cities, the layers of basalt are 3 miles thick, so almost 16,000 feet. And I mentioned that Tri-Cities sits at about 300 to 400 feet above sea level, which means that we have layers of basalt that go down 15,000 feet below sea level. It's kind of crazy to think about because it was above sea level when that basalt erupted. Say, whoa, so what? Does that mean sea level was 15,000 feet lower? No. What happened is as all of this lava was piling up on the land, the weight of that lava was actually pushing the crust down. And the Earth's crust is actually kind of trampoline-like in that heavy things will cause it to get pushed down. And when you remove heavy things, it causes it to spring back up. That's happening still in eastern Canada, where the continental ice sheet used to be. Okay, so let's get these slides back up here. How do we do it? Nope, not that. This screen mirroring. HS43. This is, sorry about this, 3571. Good. 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 Play. Set. There. Okay, we saw that. Bunch of layers. We saw that, a bunch of columns. We saw some different columns. We saw the crinkle-cut fry-shaped columns that nobody can explain those weird ripples yet. More layers. In these ones, you can see, you can kind of see in a couple of these layers. This one, you can see some entablature with the columns at the top and the bottom. In this one, you can see some entablature right through there with the columns at the top and the bottom. We saw pillow basalts. We saw columns, entablature, columns, top of the layer. You would expect to find vesicles right up here. And we can tell at the bottom of this layer that this was not erupted into water because there is no pillow basalts here. We saw the Washington State geologic map that we used in our lab. We've got our little green islands that now we've got a really clear explanation of where those came from, sticking their heads up above the high lava mark. We've got Columbia River basalts occupying the most of the southeast part of Washington State. So this diagram, if I remember correctly, came up kind of right as the bell was ringing. So this is where I'm going to pick up. There's a lot going on this diagram, but I want to point out a couple things. The Steens, that's our oldest Columbia River basalt group, something like 15% of the lavas. The Steens dikes. Dikes are another word for cracks or fissures in the ground that lava comes out of. The Steens dikes are down here in northern Nevada and also in southeastern Oregon. And the extent of the Steens lavas is down there. It's all basically in Oregon, a little bit in Nevada. Not going to find any Steens here in Washington. And then as you move northward, we've got the Monument Dike Swarm. These cracks in the ground here are from one set of eruptions. We've got the Chief Joseph Dike Swarm down here. That is where most of the Grand Ronde comes from, is the Chief Joseph Dike Swarm. So Grand Ronde, 73%, the vast majority of our basalt came out of these dikes here in northeastern Oregon and southeastern Washington. But the other thing that this particular map shows, there's two things that it shows that I really like. One, this dotted white line right here is the craton, the boundary of the craton. So geophysicists can have different tools, ground penetrating radar and all kinds of cool stuff, to know where the craton of our continent is. And thinking all the way back to our continent cross section where we had our blobs of igneous shit at the edges, blobs of igneous stuff at the edges, and a crystalline craton, metamorphic, and sedimentary platform rocks sitting on top of it. This kind of fits into that model. The craton doesn't go all the way to the edge of the continent. And here it is. So we barely have any craton in Washington. Oregon barely has any craton at all. California doesn't have any. So I like that that's on this map. And the other thing that's on this map that's a little bit of foreshadowing for us, honestly, is this trail of old calderas from Yellowstone marching off down to the down across the Snake River Plain in Idaho. that's a little bit of foreshadowing for us. This one shows some similar stuff, but is far more colorful and modern. And this, I like this because it has the different formations color-coded. So we can see Steens is light blue, Imnaha is dark blue, Grand Ronde is all the green stuff. So we can see Grand Ronde basalts all the way up by Spokane, all the way down here in the middle of Oregon, all the way out here at the Pacific Ocean. These things flowed all the way to the Pacific Ocean. Wanapum basalt, only 6% or whatever of the total amount of lava, but it covered a lot of ground. Look, Wanapum made it all the way out to the Pacific Ocean too, way up here into the Colorado Plateau, or Colorado, what the hell am I saying? Okanagan Highlands up here. Got the Chief Joseph Dyke Swarm labeled up here in this general area as well. And then the Saddle Mountains, the last 1%, still covers actually a fair amount of ground. So I like that one for that. This is far more boring. I don't expect you to memorize it or anything, but I did want to show it to you. This is how geologists organize information. The whole thing is the Columbia River Basalt Group. We've got ages in the next column from 16.7. Since this graphic was made, we've got some better dates that push that back a little bit further, back towards 17, up to about 5.5 million. Steens, Imnaha, Grand Ronde, Wanapum, Saddle Mountain. So there's our formations with approximate volumes of basalt. Polarity. As it turns out, the Columbia River basalts record switches in the Earth's magnetic field as well. That's not really that important to us. But it is one way that geologists are able to identify certain units within those. And then members. These are the members are the flows. I don't know why we don't just call them flows, but they're called members of a formation. So, for example, here's the Rosa member of the Wanapum Formation. Rosa, that's our crinkle cut. Rosa is 14.9 million years old. So, next time you're driving down the road and you see, and when you're headed towards Vantage, you can see Rosa on the east side of Highway 243 down there. You can see Rosa, and you can point out to your family or whatever. Say, hey, those rocks are 14.9 million years old. And then we've got volume of each individual flow. And then here's Grand Ronde. It's a short time span, but it's a whole lot of lava, and it's a whole lot of flows. And then this is the last picture I wanted to show you. This is one of the dikes. This is one of the cracks in the ground where these flows emerged from. And you can still see that kind of columnar, the column shape, but they're not vertical columns. In this case, this was a crack in the ground, like this, and lava was coming up like this. And we said that these lava flows, when they're on the ground, they cool from the outside in. And they cool from the outside in, and those cracks form at the outside cooling surface, and then they propagate inward. So we can see why those columns are not vertical, because the cooling surface was the walls of the crack, not the top or the bottom. And so it cooled from the walls of the crack in towards the center. So that's what these fissures look like today. All right, onward. What does it all mean, man? What does it all mean? Stop here. Okay. So on a most basic level, in order to have all of this lava, we got to have some heat. Something's got to melt it, right? Like, in order to have lava, you have to have a heat source. We went over that when we were building different volcanoes and stuff. We dry up, if we turn off the heat source, the lava turns to rock. So we've got a tremendous amount of lava. We need heat. Got to have a heat source to produce these massive amounts of magma. So this is the big question. Where did all of this come from? And in order to answer where it comes from, we have to answer, what is our heat source? So it's an opportunity to put together some concepts. Let's put this in. We gotta put it in. We have to set it in time in order to get a good idea here. So thinking about page, there's just a couple pages back. So from our Farallon plate lecture, it would have been 36. The one that we color coded, West Coast tectonics. Take a look at West Coast tectonics. Take a look at 36 and think about what's happening in Western North America 17 million years ago, right? This stuff started $17 million years ago. Yes, that'll work. That'll work. This stuff started 17 million years ago. So the closest picture we have on 36 is our 20 million year ago picture. 3 million years before the Columbia River basalt started. 3 million years is not that long in geologic time. So what happened 20 million years ago? San Andreas Fault started forming. North America started crossing the East Pacific Rise. Huh. Is there a connection there? Do we have some kind of connection with North America beginning to cross the East Pacific Rise down here in California 20 million years ago? Could be, could be. Is there anything else that this could be related to? And the foreshadowing there from that slide a little while back, you'll remember this. We have this trail of old calderas stretching across the Snake River Plain. We talked about this when we were talking about hotspots, and it was some evidence for the direction that North America was moving. And I think if you shuffle back in your notes enough pages, somewhere you have it written down how old this trail of calderas is, or when it stops. Somebody find that date for me. I'm gonna redraw this a little bit bigger. Somebody find that date for me. When does that trail of calderas stop across the Snake River Plain? Should be back there somewhere. Number of pages back. Give you another second to try to find it. Oh, I can't wait. I can't hold it. I can't hold it any longer. This trail of old calderas across the Snake River Plain, stretching from modern-day Yellowstone National Park, which is sitting on top of the Yellowstone hotspot. We can see exactly where that hotspot was, or rather, we can see exactly what part of the continent was on top of that hotspot. In this beautiful chain of calderas stretching across Idaho that stops right here in northern Nevada, southeastern Oregon, and southwestern Idaho 17 million years ago. 17. We have the time and we have the place lining up to have a Yellowstone hotspot in the same place that these Columbia River basalts start. Right? Those Steens dikes are right down here. Northern Idaho, southeastern Oregon. Steens Columbia River basalt, 17 million years ago. Now you might say, now wait a minute. Why do we have basalt lava? And how would basalt lava be connected to this Yellowstone hotspot? Yellowstone's making these calderas, man. Yellowstone is making super volcanoes. It's melting continental crust. It's making the stickiest, gooeyest magma that there is. None of that gas can escape. It builds up tremendous pressure. It blows up. It kills everything in 100 miles. And now we've got this super runny stuff too. Like, what? But the time and the place match. And so that's a big clue. Yellowstone hotspot and the Steens dikes are in the same place at the same time. But now this doesn't really, you know, caldera chain starting 17. We've got our CRBs starting 17. They both begin in the same place, but they drift away, right? They separate. And this gets even weirder. Columbia River basalts, I'm going to use blue for all my Columbia River basalt stuff. Columbia River basalts, those get younger going north up into Washington. Yellowstone hotspot, that gets younger going to the northeast and now is in present day Wyoming. So this is a puzzle. This is a strange thing. But they both start in the same place at the same time, and there has to be some kind of connection. I'm not going to tell you much more. I want you to think about that. I want you to chew on that for a little bit. But do we have a hotspot connection? If I'm a scientist, if I'm a geologist, and I'm putting these pieces together, and I'm saying this Columbia River basalt stuff started in the same place at the same time that this Yellowstone hotspot was there, could there be a hotspot connection? The next obvious thing to do is to say, well, is there anywhere else in the world that has these flood basalts? Do we have flood basalts anywhere else, or is this truly unique? And as it turns out, we do have flood basalts in two other places. In India, there's a place, a formation called the Deccan Traps, D-E-C-C-A-N, Traps. Enormous flood basalt province, bigger than the Columbia River basalts, much bigger, in fact. Biggest flood basalt province in the world. I can't remember the date off the top of my head, but I want to say 46 million years ago. Somewhere in the 40 to 50 range. But in India, the Deccan Traps are bigger than CRBs, even more basalt, like maybe even twice as much. There's one more flood basalt province in Siberia. I don't know the name of it. It's probably in Russian. And I don't know the age of that one, but it is also bigger than the CRBs. Like, as flood basalt provinces go, ours is kind of small potatoes. But it is older and larger than CRBs. Older and larger than our flood basalts here. So we do have some evidence elsewhere on Earth. We're not completely unique. People come study ours because they're the youngest. They're the freshest. But if I'm a geologist and I'm trying to find a connection, could it be that these flood basalts are related to this hotspot? We're going to go look at these flood basalts here, And here, say, well, are they related to hotspots? And the answer is yes. Both the Deccan traps in India and the ones I don't know the name of in Siberia are related to hotspots. Just like Hawaii, just like Yellowstone National Park, just like the Galapagos Islands, just like Iceland. Iceland sits on top of a hotspot. So, there's some evidence that there could be a hotspot connection. You got a hotspot in the starting location, in the right place at the right time. Another interesting thing, and this is kind of peripheral, but you might be interested. Both of these events, India and Siberia, both of these events are tied to mass extinctions. One of the ways the geologic record, geologic time is organized is by life forms. It's organized by the animals and plants that are alive in a given period of time. And as it turns out, significant numbers of organisms disappear from the fossil record, coinciding with both of these. So is there some connection there? We might leave this class period with more questions than we have answers for. I'm almost certain we're going to. Do we have a connection between flood basalts, hotspots, and mass extinctions? If I'm a scientist, what am I going to do? I'm going to go see if I can find mass extinctions happening 17 million years ago. Do I know? Personally, I do not. I don't know if there's a mass extinction associated with the Columbia River basalts. But the Columbia River basalts are also much smaller than either of these. So it might be harder to tease that data out. Last point that I would like to make with this is it's hard to put this story together. This is a tough story for geologists to put together, and one of the main reasons for that is because there's nowhere that we can go to see all of the Columbia River basalts in one place. I talked about a big layer cake. I talked about a big German chocolate cake, or a big cow pie of layers of basalt sitting in the middle of Washington and Oregon. But the old ones are down here. The younger ones are up here. We got some that made it all the way out here. We got some spots where, there will be a flow that covers everything, and then there'll be a flow that kind of peters out, and then there'll be another flow, and then there'll be a flow like this. And so, so you could do another one that kind of peters out like that, and then we could do another full one. And so it's really challenging, because if this is 1, 2, 3, 4, 5, 6. If I'm a geologist and I'm going out to study these things in the field, if I'm looking right here, I've got flow 1, 3, 4, 6. If I'm here, I got 1, 2, 4, 5, 6. Maybe there's 7 and 8 and 9. because every eruption covers a slightly different area, I can go here and get 1, 3, 4, 5, 6, 9. So it depends on where I go, which basalt flows I'm going to see. There is not any single place where we can see, even in Tri-Cities, where we can drill straight down and get a record of 3 miles of basalt. There's still, you're not getting any of the Steens basalts down here in Oregon. So it's a really challenging thing to study, and it's taken geologists a long time. Geologists are still putting this story together. This is not settled science. And really, I want you guys to understand, most science is not settled, not considered settled. There's more to learn about everything, and there's a lot of geologists who are still working on putting this picture together. But from
Can we please have Daisy Barajas, Aura Caro, Miguel Castro, Valentina Castro, Belinda Contreras, Kimberly Contreras, and Noemi Hernandez come to the office? Thank you.
But from today, we can walk away confident, knowing, well, maybe not knowing, but we can walk away with some degree of confidence that there's something to pursue here. There is some questions to be asked and somehow a puzzle to be put together about the Yellowstone hotspot, where it was 17 million years ago, and what connection it has to our lavas here in Eastern Washington. So with that, I hope you guys have a wonderful afternoon. And we'll see you. It's Thursday, right? We'll see you tomorrow. Awesome.